Okay, so this video is dedicated to partial derivatives. So previously I made a video on regular derivatives, basically derivatives of functions where it's mapping one variable, let's say x, to another variable y, and we have that in our coordinate plane. But there are other functions where we can map maybe three variables to one, like w equals f of x, y, z. We have three variables, x, y, z, and we map it to some function on a graph which will represent some shape. So how can we take the derivative of that with respect to each variable? Well, we have to use partial derivatives. That's kind of the whole point of them. So how a normal derivative is notated only works when you're taking the derivative in R2 with respect to one variable, where it's a one variable defined function mapping one variable to another. When we have some function with respect to x, y, and z, the partial derivative of each variable is denoted as the partial of f of x, y, z over the partial of the variable. It's very easy to write down and notate. You just have to know that symbol. So if our function is, let's say, f of x equals 3, if f of x y z, it's important to say, is equal to 3x squared plus 5y cubed plus 64 to the fourth, well, then using the partial derivative with respect to x, y, and z, um, basically what we're going to do is we're going to take the derivative with respect to each of those variables and treat all the other variables as constants because we're basically looking at the rate of change in that direction. And each of those components just contributes to a direction in this 3 space, which we call it R3. So I wrote down the derivatives there, 6x, 15y squared, and 24z cubed. You might already be able to see what I was talking about. It's just the constants, and it's growing by that rate in each direction. And how it's written here, it kind of just shows us the components, even though z is growing faster than y and y is growing faster than x, and that's why the partial derivative of z is greater than that of y, and that of y is greater than that of x. So what we can do several things with these. Basically, we can help to find certain things of three-dimensional graphs that will help us determine the manner of the graph and what it looks like similar how we would use one-dimensional derivatives to help us look at the concavity, the rates of change, and even like limits of certain graphs using in three dimensions, even though it's more complicated than. So let's say we have a case where we have multiple variables being multiplied by each other. Here we have x, y squared, and z. In order to take the partial derivatives, we would have to treat the variables as separate beings. But when we take the derivative to one variable, the others are just constants. So like if we were trying to do the partial derivative of f with respect to x, y squared z would just be another constant. So the whole constant term could be factored out as 15y squared z. And then the derivative would just with respect to x would just be 15y squared z because the x is constant. So you see it there. Now when we take the derivative with respect to y, we just have 2y times the constant term, which is the whole 15xz, everything that's left over, and we get 30xyz. Same with the z, except we're just basically taking the z away since it's a first degree term. So like each of these results basically show us how fast the graph is changing in the direction with relation to the components. And since they're all being multiplied here, it's not necessarily in respect to one component. It might be multiple components, but it is in terms of the original graph. Like the rate of change in the z direction would be the graph divided by z, the function divided by z, since it's just z% less. Okay, so now that we can find partial derivatives, but why do we need to find them? Like, what's the practical application? Everything in math, or most things in math, have practical, real-world applications. Well, even though partial derivatives are considered higher level math, they do have several applications. The first one is called a gradient. So basically, a gradient can be thought of. pretty simply in a lot of real world like um, real world complexes. So basically, let's say you're scaling a mountain and you want to find what is the quickest way up this hill from my current location to see the greatest rate of change to get to the top. That would be your gradient, the vector that gives you the correct direction and magnitude to see the greatest rate of change. So you could also think of it if you have a hot dish and you stick your finger in the center of the dish and you want to find what is if I move my finger, what is the fastest rate of change from this hand that I can move it in that direction to see the greatest rate of change. And when you get the vector, the inverse tangent of the y component over the x component, or in three-dimensional dimensions, it would be spherical components, but it would give you the direction, theta, and then it would give you obviously a magnitude, the square root of the sums of the squares of the parts. So we can do that, but we can also use these gradients and partial derivatives to solve difficult three-dimensional optimization problems. So basically, instead of doing related rates in 2 dimensions, we can scale it up to 3 dimensions, and it makes it very easy. On top of this, we can use that optimization material to use something called Lagrange variables, where we can set specific domains on things, and we can set them equal to each other to try to find bounds. If we know our bounds, and then we can set random variables equal to each other, and that's one way of doing optimization in three dimensions. Another thing is we can find basically how fast satellites are moving with respect to stars based on the partial derivatives of the respective motion to each star. And so it basically forms um, a very good application in real life. So I recommend that you really get used to them. Okay, thanks for watching and have a good day.